Hi, are you planning on doing some low resistance measurements with your digital multimeter? Today I'd like to share with you some tips and tricks on performing those low resistance measurements with the DMM6500 graphical sampling multimeter. Let's begin. First, we will briefly review Ohm's law as it applies to a standard two-wire measurement. Then we will examine why this can be problematic for low resistance values and provide a demonstration of this error. Finally, we will identify the corrective solution, the four-wire measurement method, and the details about how it works. Again, we will conclude with the demo of the four-wire measurement method in action. The resistance function of your typical ohm meter or multimeter will source a known current to your device under test, the resistor, and perform a voltage measurement at the terminals where the test leads are inserted. The resistance value is calculated using the sourced current and measured voltage values. When your resistance values are greater than 100 ohms, this is probably fine. However, when you start measuring lower resistances, you will notice that your measurements hold some error. Your test leads are wires with very low resistance values. Because the voltage measurement is taken at the terminals of the multimeter, these very low resistance values of your test leads are factored into Ohm's law and offset the measured total resistance. If you are a designer of a product that uses a low resistance, this may not affect you. If you require a shunt resistor for your design, you simply select the part from a distributor that meets your needs, relying on the specifications provided. However, you may need to account for other low resistances in your design, such as the traces on your printed circuit board, which may contribute to performance inefficiencies. If you manufacture low resistance devices and need to guarantee that they meet the specifications you will be providing to potential customers, then obtaining the most accurate measurement of your device is imperative. Consider the situation where you are making 50 milliohm resistors and your test setup uses leads that are 10 milliohms each. This has the potential to result in 40% error in what you are measuring. Let's start by making a common two-wire resistance measurement. As you can see on the right-hand side here, I have my high and low terminals connected to my test leads. I have a selected device under test, which is 50 milliohms with a 1% tolerance, meaning my low and high values are 49.5 milliohms and 50.5 milliohms. Therefore, the resistance value I measure by my meter should be about somewhere in between those. So let's go ahead and connect the device under test. And we will select two-wire resistance. And as you can see, I'm just about double what I am expecting from this particular device. I can change the position of where the leads are connected, but that doesn't make much of a difference. Let's investigate how to correct this. Let us examine how to achieve the most accurate measurements brought to us by Lord Kelvin. In this configuration, we see a second set of multimeter terminals, the sense connections, as well as an additional pair of leads which must be connected closest to the resistive element body. You may reason that this will impact the calculation of Ohm's law as follows. While you now have a second set of test leads in your setup, we can consider the following. The RSense input is a very high resistance, and because it is in parallel with the load, its impact, along with that of the sense test leads, on the measurement is negligible. This allows for the measurement to be made directly at the device under test, and in doing so, we eliminate the error that the main leads have on the measurement. Let's perform the four-wire measurement. The first step is to connect my second set of leads to the sense inputs on the front of the DMM6500. I then use those leads to clip very closely to the resistive body of my device under test. I can then change my measurement function to four-wire, and you can see that we are very near the target value of 50 milliohms. Let's see if we can make that a little more eye-pleasing by applying a filter. You might be able to see in the text down here that we have a 10 sample filter applied. It's a repeating, so it will capture 10 readings and then give you an update. I want to smooth that out a little bit more, so I go to Menu, Calculations. Let's adjust my filter, and I want to make it a moving filter with a count of 100. Let's return to the home screen. Now you see we have a very smooth output of what we are trying to measure, which is our device under test of 50 milliohms. Notice that we are within the 1%, so just above the 49.5 milliohms of the lower limit.